afternoon, everyone, and welcome to this talk, Keeping Up with Java. I'm Sander Mak, and before we get started, I would like to tell you that if you have any questions, please use the app, so Jörg here can curate them towards the end of the presentation, and so that we can have a sort of streamlined Q&A afterwards. For now, we're going to talk about how to keep up with Java. And if you think about it, it's quite a weird title, right? Because it used to be the other way around, where Java had to keep up with us, because we were only getting a major Java release like every 3 or 4 years, and it seemed like Java was sort of stagnating as a big enterprisey language, slow-moving, etc. But all that has changed. And the question is, what does that mean for us? So we'll be talking about that today. And I want to do that by looking at all the new features that have been introduced since Java 8, because who here is developing on Java 8? Right, almost the whole room. Who here is developing on Java 9 or later? Couple of hands. So that's exactly what I want to talk about, because we need to talk about adoption as well. So first we'll look at features, and then we'll discuss about adoption. How can you get from Java 8 to later versions? Obviously, we can't cover everything, but we'll see the highlights of the features. So a little bit about me. As I said, my name is Sander Mak. I work with Luminis, which is a software technology company in the Netherlands. We do both product development and consultancy. I'm mostly involved with the latter. And in our products, we were also very, very heavily invested in modular architectures. And we used to do that a lot with OSGI. You may have heard of it. But when Java 9 came along with a module system, which is sort of the biggest feature that happened to Java since a long time, then me, together with a coworker, dove quite deeply into this, which also led to this book, Java 9 Modularity. And this will also be a big topic when you move from Java 8 to a later version of Java, because you will encounter some way or the other the module system. But we'll talk about that. So obviously I speak at conferences. I also do some Pluralsight work, so if you have a subscription there, highly recommend checking out some of the courses I did on Java 9, 10, and 11 there. With that out of the way, let's just move on to whatever happened. And we'll do this in a chronological order. So we'll start with Java 9. And as I said, the biggest feature in Java 9, which was, by the way, released more than a year ago now, so in September 2017, the biggest feature there was the introduction of a module system. So what I want to do now is give a quick overview of the features of the module system, and also show you a demo of what it can do. And then we'll talk a little bit about the impact on existing code bases, because, well, you can develop applications from scratch using modules, but there's also some considerations if you bring old code to new versions of Java. So we'll look at that as well. So in essence, a module groups packages. And what you can do is you can create a so-called module descriptor in a file called moduleinfo.java. And in this module descriptor, you can be as simple as this. Only use the module keyword, give a name, an identity to the module, and that's it. Then every package that's part of this source tree, part of this module, and we'll look at how that looks in code later. Every one of these will be inside of this module main that we have here. So obviously, this translates into something at runtime as well, because modules don't only live in source code, but they are also represented at runtime. And there we see that we might have a module at runtime called main, because, well, that's the name that we gave to the module, and it contains the packages main.web, main.persistence, and main.integration. So far, so good, but if you're thinking about modular development, you don't think about single individual modules. Systems arise where modules work together. So what you can do with modules is you can also explicitly declare relations between modules in the Java module system. So let's say our module main requires some code that's in another module called helper. So what we can do is we can say, okay, this module main requires module helper. And module helper, of course, also has a module descriptor with a name. And through this explicit dependency, both the compiler and the Java runtime now know that there's a relation between these modules. And this used to be the case between jar files as well, but you couldn't be explicit about relations between jar files. We needed all kinds of tools around in the ecosystem, like Maven and Gradle, to handle this for us. Because, well, the JVM and the compiler really don't know anything about relations between jar files. So with this, these relations are now explicit, and they can also be exploited. For example, if you would start this application with these two modules, and the helper module would not be there, then the JVM will tell you, okay, please go fix this before I even run a single line of code, which is quite different from the class path situation, where if you had a jar file that needed another jar file on the class path, and there was only one jar file there, then it would happily start your application until it needs a class from the different jar file, and then it blows up at runtime with a class not found exception, for example. And similar stuff happens when you have, for example, duplicate entries of jar files on the class path. In short, the class path really had many issues, and modules solve a great deal of these issues. So we can have modules, they can have dependencies. What else? Well, it turns out that if you want to create a module that exposes code to other modules, you need to be very precise about what is exposed to the outside world. As I said, a module is a combination of packages, but if you have a dependency on a module, then you cannot just use any code in any package that's inside of this module. You, as a module developer, have to be very explicit about what is the API of your module, so what is public and what is not public. And in this case, in our helper module, if we want to expose code to the outside world, we do this using the exports keyword. So here we tell, okay, anyone who uses the helper module can only use types from the helper.api package. If there are any other packages in this module, then they won't be visible, which is the third construct that the module system introduces, which is strong encapsulation. Now, what happens if you have an additional package in the module helper? Well, by default, all packages are strongly encapsulated. So you can hide your implementation details and only expose the APIs that you want to expose, which is, of course, very helpful when you want to design systems that last for a long time, that you can evolve over a long time, where you can evolve the implementation details without any of the consumers having dependencies on these implementation details. I guess we all know this from theory and from practice probably as well, but now in the module system we have a very clear-cut way to do this. And if you think about this, this is really similar to what you can already do at the class and the object level, where you have private, protected, and all these access modifiers. You can think of modules as doing something similar, only at a much larger level of abstraction. So these are just the mechanics and the theory. So what I want to do is show a quick demo of what this looks like in practice using Java 9 or later. Because even though the module system is delivered in Java 9, it's still the same, it's still there in Java 10 and 11 and all the future versions that will be coming. So this demo consists of two modules, and the first module is a command line interface module, which just interacts with us from the command line. And the goal of this application is to read in a piece of text and to analyze the text with a given analysis algorithm, and then subsequently we want to present this result to the user again on the command line. And we want to separate the analysis from the command line module. So how we're going to do that? Well, I'm going to create two modules, of course. And as you can see, I now have a source directory, and inside my source directory, I don't directly have my package structure. No, I have two module directories, which correspond to the modules that you saw on the slide. So inside of a module directory, we find our typical package hierarchy. So here's a single package containing a single class, and Flash Kincaid is a particular text analysis algorithm. But there's also a module descriptor. And in this case, it's still fairly empty, right? We only say module easytext.analysis. And a similar thing happens for our CLI module, where we say, okay, easytext CLI, it has a main class, and it has a name as easytext CLI in the module descriptor. Now, just to show the code, there's nothing special here, just plain Java code, a main class that prints some help text. If we use it wrong, it gets the path, we're reading the file from the path, then we chop the strings into sentences, and we pass this to our Flash Kincaid analysis class, which comes from a different module. That's something to keep in mind. So how would we go about compiling this? Well, there's a new flag in the Java compiler as of Java 9 and later, the module source path, which understands this layout, having multiple modules in a single source folder. We also pass in the out flag, and people often forget this because we use build tools like Maven and Gradle who hide this for us, but you must pass all source files that you want to compile to a Java compiler. So we do this using our little Unix trick here with find, which passes all these 4 Java files to the compiler. So what happens now is we have a main class, which is public, which uses the Flash Kincaid class, which is also public. So it might seem that if we compile this, everything's fine. But because we use modules, we have more guardrails in place now. And that means that this module does not express a dependency yet on the analysis module. If we want to use code from there, it needs to be a deliberate decision, and we need to record this dependency information in the module descriptor. So we can say requires easy text, there we go, dot analysis. And if we do that, the error now reads, okay, this package easy text analysis is declared in the module easy text analysis, but module easy text.cli does not read it, which translates into does not depend on it. So we fixed that, and if we save the file and now recompile, you might think, okay, it should work now because we have the dependency, but then we haven't taken into account the strong encapsulation yet. Because by default, like I said, if you don't mention anything in your module descriptor, then it will be strongly encapsulated. And in this case, we want to export this package. And here we use a package name because exports are at the package level. Excuse me, and then I also need to include Java Modularity, easy text, dot analysis. So what I'm saying here is I want to expose all code that's in this package from this module to any other modules that might have a dependency on easy text analysis. And once we do that, we have all the information in place to have 2 successfully compiled modules, which we can see here in the output directory. And as you can see, the module info class is also preserved for use at runtime. So what we can do now is we can run this application, and instead of using the class path, we're using the module path, and we point it to our out directory, which contains these compiled modules. And we're going to start a module, and in this case, we're going to start the easytext.cli module. And because I haven't packaged it yet into a jar file with an entry point, I need to also explicitly define the main class that I want to run. And if I do so, I get my welcome text, and I can provide a test input. There we go. And we get a flash concave score of 83. So this works. So we now have 2 modules that we compiled with explicit dependencies, a strong encapsulation. But I might hear you think, okay, class path, module path, what's in the name? Well, there is definitely a functional difference between the 2. Because if I now remove, for example, this easy text analysis module, so the compiled module, and I'm not going to recompile again, I'm just going to issue the run command again of my application, then what happens is that Java won't start my application. Instead, it sees the module descriptor of the CLI module and says, okay, I need this easy text analysis module, so please first fix your module path before starting this application, which is a big improvement over the class path, which would just start our application and then just blow up at some point where it needs another class, which would be fairly quickly in this simple example, but if you have a large and elaborate application, then it might blow up at any point in time, which is bad, of course. So that's about modules and using them in this way. Now, lots of more can be said about the module system. We won't have time to go into that in this talk. I do have several talks online as well at YouTube that go into depth about using, for example, services to decouple modules even more. So highly recommend it if you're interested in this. But I do hope this shows that we now get a module system in Java that's native to the platform, that allows us to express dependencies between parts of our applications, and also to be very smart about what's public and what's encapsulated at the module level. So you might wonder, okay, sounds very cool, but why would you want to do this? And actually, if you look at the history of the module system in Java, then the reason why they started developing this is actually quite selfish from the JDK and the Java team side of things. Because what happened is that the JDK itself is more than 20 years old now, and it actually was a big monolith, a big ball of mud, you could say. There was this rt.jar file, the runtime jar file, containing tens of thousands of classes, and they all had sort of dependencies that weren't very visible and that also weren't very good in all cases. And the JDK also had the problem that there were lots of internal implementation classes. People often hear about the sun, misc, and save class, to mention one, but there were many others as well. And people started using these in the wild. And we all know that Java is very big on backward compatibility. So what happened there is that they effectively couldn't change these classes because so many people were using them, sort of stalling the evolution of the whole platform. So to address these issues, they started with modularizing the JDK. And what you see here is the end result of the modularization of the JDK. Again, lots to tell about this, but not for this talk. But in the end, what modularization gained them as a big Java code base is more maintainability and flexibility, and also a reliable composition between different parts of your platform because of these explicit dependencies. It's much more reliable than the class path, as we saw. So these were main drivers for the JDK itself. And of course, this applies to any large code base, right? If you have a code base that you maintain for years, maybe even decades, then it really pays off to have a clear structure both in your code and not just in your head or in your documentation, but also in your code with a module system that helps you enforce this. So what this effectively means is that you want to decrease the model code gap, right? Because we can all draw these very nice architecture diagrams on whiteboards. I hope they're a bit nicer than this single point of failure design, but anyway, you have a whiteboard design, and you can take this and actually translate this into modules that have the same names in your application, that have these explicit dependencies that are the same as the arrows that you draw on the whiteboard. And that can also warn you if you violate these dependencies and start using code from modules that you shouldn't use, or start using encapsulated code that you shouldn't use, because you can't do that in the module system unless you explicitly tell the module system that it's okay. So this is really one of the goals. And just to illustrate this a little more, I also want to show you a modular application in IntelliJ. So this is the same easy text application, only expanded much further into more modules, more functionality, different analyses, etc. We're not going to look at the whole example. I just wanted to show you that the tooling is already there. As you can see, IntelliJ, but also Eclipse, they support module descriptors. They know about the module system. They know about these explicit dependencies between different modules. And what's actually really cool, at least I think it's a really cool feature of IntelliJ, is that you can also look at a diagram. In this case, you get the option to look at the Java modules diagram, which visualizes all the information in the module descriptors. So what we have here is a very nice way of seeing how our code base relates, where we have dependencies between modules, and the blue one is an external library, by the way. The yellow ones are all application modules, and the light yellow ones are all modules that live inside of the JDK. So you can very well see that our EasyText CLI module doesn't have that much dependencies, but our GUI module, which is written in JavaFX, has dependencies on all these JDK modules that you can now neatly see in this module graph. So I think this really illustrates the point of it's not only good to have this information on a whiteboard or in documentation, but also to encode this in module descriptors and have the module system work for you. Another great tool that was enabled by module descriptors and the module system is jlink. And what that solves is the issue that we all probably know, that if you want to distribute a Java application or run a Java application, you also need a JDK. And the point here is that this JDK is very big, right? And it contains all kinds of technologies that your application may or may not need. For example, if you have a web application, well, you probably don't need all the desktop, Swing, and JavaFX APIs, etc. But they're still all there, and they're pretty big. So JDK is typically around 300 or 400 megabytes, and your application itself is much, much smaller. So what you can do with jlink is, if you have an application that is modular, then it expresses all its dependencies explicitly, not just on your own libraries and application modules, but also on the modules that you use from the JDK. So what jlink can do is it uses these explicit relations to calculate a small subset of the JDK, the minimal subset of the JDK that is necessary to run your application. And then it actually outputs this into a so-called runtime image containing the JVM and only the modules of the JDK that your application needs. And it also bundles your application modules and everything that's necessary to run your application. So that you get a very, very self-contained and small runtime image that you can use. And you can use this, for example, as basis for your Docker image, rather than shipping around larger images containing full JDKs. Or if you're in the IoT space, it also helps if you have smaller deployments and smaller things to shuffle around. So this is really something that's enabled by the module system. So what about impact on Java 8 code bases if you move to Java 9? Because we saw a lot about the module system, but it's also good to know that using modules and module descriptors is optional. It's fully optional, so you can still also use the class path if you're moving beyond Java 8. Of course, you won't get the benefits that I talked about, but that's just a choice that you have to make. And in a lot of times, it makes sense for existing code bases to stay on the class path. Not all code bases are really modularized already, and then it will be very hard to untangle them if you want to directly move to a newer version of Java and also move to modules. So let's assume that you have a class path-based application and you want to take it beyond Java 8 to Java 11, let's say, which is the current version. So what still is the case is that underneath Java 11, even though your application is using class path, the JDK itself is still modularized. And this is something that you will encounter, because the JDK has actually encapsulated a lot of types that were previously sort of publicly visible and used maybe not by your application code, but most likely by some of the libraries that you're using. So what happens if you run this code that was compiled on Java 8 on Java 11, for example? Well, fortunately, it still runs because, like we said, Java is very big on backward compatibility. But it might generate warnings when running on Java 11, telling you, okay, so this code is actually using an API that has been encapsulated in this version. And at a later point in time, we may also disable this for the class path, and not just for other modules, for modular applications. So these are runtime warnings that you can run into. Also, if you try to compile any new code that still uses these encapsulated APIs in the newer versions of Java, then it won't compile. It won't allow you to introduce new legacy code that uses these encapsulated APIs. So there's a big difference between running on Java 11 and actually compiling and building on Java 11, at least if you're using these encapsulated APIs. Another big thing that happened between Java 8 and now Java 11 is that some of the enterprise APIs that typically were in the JDK are now removed. And they're listed here. It's Corba, well, I don't think anybody misses that, but also JAX-B, for example, and the XML web services stack. These have all been removed in the sense that they're really EE technologies, so they belong to Java EE, which is now Jakarta EE. And this move means that if you have applications that use these libraries and that depend on them being there in the JDK, you will now have to bundle your own dependency that implements these APIs. So they are gone in Java 11, and you will need to take care of that. Of course, if you're using an application server, then the application server will provide these implementations, so that's not a big deal. But for example, if you have a standalone Spring application using Spring 3 or Spring 4, it heavily depends on JAX-B. And it's just not there in Java 11 anymore, so you would have to add this to your class path yourself. Fortunately, they fixed this in Spring 5, so if you're using Spring 5, you're good to go. And this applies to most libraries, by the way. If you're moving to Java 11, it really pays to upgrade to the latest versions of all the popular libraries, because they are pretty much ready for Java 11 by now. So that was the module system, but there was more in Java 9. It was actually a pretty big release. For example, there was a REPL. Who knows what REPL stands for? Yeah?
Read, evaluate, print loop?
Exactly. Read, eval, print loop. But I can imagine if you don't know this acronym, it still doesn't mean that much to you. So JShell is actually a tool that allows you to enter code in a sort of a shell environment. So the read part is inputting code, and you press enter, and it immediately runs the code. It also gives you back the results, and you can do this again and again to refine your code. So it's really a nice iterative tool to work with Java code. So I wanted to give a quick demo of that as well. So here we have a shell, and I'm going to start JShell. And of course, we all had the Vim experience of starting Vim and not knowing how to get out. So I'm going to tell you first how to get out of this. There's a /exit command, or you can alternatively also use Ctrl-D. Ctrl-C won't work. So you can do that to get out of JShell. But JShell is a place where you can execute Java expressions and Java statements. So what's the simple expression? Well, this is the simplest one, of course, that I can think of, and we get back a result. Now, obviously, you won't fire up JShell to do calculator stuff, but once in a while, you're maybe bit shifting and you're thinking to yourself again, oh, what was it again? So somebody wants to take a guess what 4 left shift 8 is? No? 3, 2, 1. It's 1024. So you can also see that we get a sort of generated variable name here, and we can use that in later expressions. So if we shift it back again, there we go, then we're back at 4, which is nice, of course. You can use Ctrl-L, by the way, to clear the screen, but you can't just use expressions, you can also use statements and call methods. For example, system out println, like this. Hi Berlin, there we go. And it works as expected. We have history, so we can go back. And the interesting thing also is that JShell also supports tab completion. So if I do this, print, and then do tab, I get all of the completions that are available. And if I do println and do an opening brace and do tab again, then it actually shows all the overloads that are in the API. And it says if you press tab again after this, then you get to see the documentation. So it's also a very, very nice tool to interactively explore APIs, which you probably often do a lot. At least I do it a lot. So we have here an interactive coding environment with code completion, but also documentation. So who noticed something when I wrote this? What's different than normal Java? There's no semicolon. Exactly. So you can do this, but you don't have to do this, which is nice, just a little time saver. The other thing that's different may be apparent if you see this code. So what's different than in normal Java here? Exception, exactly. So you don't have to worry about exceptions. It will be handled for you by JShell. So again, these are just small things. By the way, if you're doing this, as you can see, this thread.sleep happens in the foreground thread. So if you want to break out of this, you can do so using Ctrl-C. So that's good to know as well, if you have a long-running computation there. Now, one last thing I want to show. You can do lots of stuff, but you can also, for example, declare a method in JShell. So what I'm going to do is I'm going to create a method that, for a given class, there we go, gives back the module that the class lives in. And as you can see, I get a second line because I have an opening brace and no closing brace yet. I'm going to say return class dot get module. That's a new method that's introduced to check where a class lives, in which module. And if I close it, it created the method for me, and I can even use tab completion again to use it. So if I ask, okay, where's this string class? Well, that's in module java.base, which is sort of the module that contains all the foundational types of Java, like string, object, collections, etc. Of course, I want to check whether it really works and see if we have the Java util.logging.log manager class, for example. And indeed, it gives us back that this lives in the Java.logging module. So this seems to work, which is very nice. And if I want to get an overview of the methods that I have defined so far, or the variables that I've defined so far, I can do so. And I can refer back to the variables, like I said. You can even create your own named variables like this, and then it will be usable just by the identifier. So this is really a versatile tool. I don't use it every day, but I fire it up about once a week just to try something out, to try a new API, or to just fine-tune a piece of code, maybe a Java regular expression, which are notoriously hard to get right the first time. So things like that are very useful to do in JShell. All right, let's move on, because there was more in Java 9. For example, collection factory methods. We probably all know this kind of code. If you have a small collection with predefined elements that you want to define, you usually do something like this. And while this works, it's not very pretty, right? Because we need to think about an actual implementation type that we're going to use for the list. We need 3 statements to add and 1 statement to create a type. So this is very hard to do as a field initializer in a class. All in all, could be better. So as of Java 9 and later, it is better because we're getting these collection factory methods. So what we can do now is we can say, okay, list of, and then just provide the elements that we want in the list. And the same can be used for sets and for maps. So I want to do a quick demo of that as well. Of course, using JShell, what else? And just to drive the point home, this is how you create a list now. We get the elements back. If you put in a null value, which is a bad ID in a collection, then in this case you will actually get an exception when creating the list instead of being bewildered by the behavior when using the list. The same actually applies to set, and the addition that set has is that it's unordered, of course, so you can see that here. We get back 213. And also, if we have duplicate elements, it's not allowed in the set, so you get an exception for that as well. So map.off works similarly, but in this case it has a key and a value parameter, and then again a key and a value parameter. And this way you can construct a small map using these collection factory methods. The interesting thing here is that, of course, you don't have to think about any implementation types. You just get back whatever the factory method, the off factory method, thinks is best for you. So if we do this, for example, for the empty list, and then we asked for the implementation class that's underneath, you can see that there's a list n implementation in immutable collections, which wasn't there in Java 8 and earlier. So this is a very specialized implementation. There's also a list 1-2 implementation for single or double element lists, which is highly optimized, just containing fields rather than an array internally. But you don't have to think about this. You just call the factory method and you get back the best one that fits your use case, which is really nice, of course. And if you want something else, you're still free to use a linked list or a array list or whatever you can construct yourself. These are just really convenience helpers for small predefined collections in your code. All right, so that was Java 9. Let's move on to Java 10, which came 6 months after Java 9. And we'll talk about it later as well, this release schedule. But in Java 9, we actually got a new language feature. Java 10, we got a new language feature called var. So what does var do? It's about local variable type inference. So we're talking about variables, like this one, but not just any variable. It must be a variable inside a method, so hence local variables. And what we can do as of Java 10 is replace the type of the variable with var. And no, this does not mean that Java becomes a dynamic language, because the type will still be inferred by the compiler. So it will still be a name variable with type string, only we don't have to type it out all ourselves. So it's not a big feature. If you're doing JavaScript, you may already be used to this, or even C#, which has this feature as well. But now we have it in Java. Should you use it everywhere? I don't think so. There are good users and there are bad users so far. We won't go too deeply into it now. But if you have pieces of code like this, where you have URL is new URL, well, that doesn't make that much sense, right? There's lots of repetition there. And the same for URL connection, URL.open connection. It's all kind of messy and obvious. So you could change this to this piece of code. And look what happens. You put the focus not on the types, but on the variable names. And if you choose these variable names wisely, then at least my personal belief is that code can be much more readable. That doesn't mean that you should go out and replace every type in your local variables with var. But just be aware that if you're using Java 10 or later, then you have this new tool at your disposal. And just to do a quick pub quiz, and to show also that var is not without dangers, let's do this. Okay, what will be the type of this? I'm going to let you guys play compiler for a little bit. Int. And let's set feedback for both. So we actually see the type. Yeah. So we got a variable of type int. Now, what would be the type if we were going to do this? Double. Well, we have some people who are actually knowledgeable here. Very good, but not everyone knows that this literal translates into a double. So you need to take care of this if you're doing this with strings. It's obvious that it will be a string, but do all people know what the other literals do in your code? Good question to ask. So let's do This one, what do you think the type will be? Exactly, exactly. It will be possible to give this a type, but it would not be a useful type. So actually, this is not allowed by Java 10 and later, which is good. But let's do something slightly more complicated. So let's say a list of where we put in int, and we put in this double, and we put in a string. So what would be the type of this? List of objects. Anyone else? Something else? This looks very impressive, right? So it's a list of something that's both serializable and comparable, which again extends serializable and comparable. This is a type that you cannot express yourself in source code. But the compiler is smart enough to deduce this type. So this is sort of unexpected, right? And also goes to show that, yes, it's a simple feature, but it can lead to some counterintuitive results. So a last one. Let's say we want an array list. And we say, okay, new array list. But we're going to use the diamond feature that we got in Java 7. So what would be the type of this? No one? Sorry? Exception? No. Actually, this will be an array list of objects, which is probably fair enough, but also probably not what you would want. So in this case, always make sure that you provide a generic parameter here as well, or just use the explicit type and keep using the diamond on the right-hand side. So again, even though it's a simple feature, please think it through before using it. And there's a very, very good guideline also by Oracle itself that's been put out by Stuart Marks. So also read that if you start using this feature. Okay, that brings us to Java 11, which was released quite recently, September of this year. And actually, what we see there is that there's one big new API that was introduced. And this was even already introduced in Java 9, but it was only an experimental feature in Java 9 and 10. It has become official API in Java 11. And it's a new HTTP client in the standard library. It replaces HTTP Euro connection, which is good because that was a really, really horrible API to work with. That's why we got the Apache client and all the other libraries that we're currently probably using in our code bases. And this one is actually fairly nice to work with and also quite modern. It supports HTTP2, it supports WebSocket communication. It even has a reactive stream built-in support, and that all just in the JDK, which is pretty great. So what does the API look like? There's an HTTP client, which has the two most important methods are send and send async. You can either get a default client or use a builder API to build a client with all the settings that you want. And in this send and send async method, the most important parameter is an HTTP request. And again, this has everything that you would expect. A request has a URI, headers, a method, so get, put, post, etc. And also, this one can be created using a builder API. And then, of course, if we have a request, we also need a response. And there we see all the things that you would expect as well. And this leads to an API where you can pretty easily create an HTTP client using just plain Java. So we get HTTP client.new HTTP client for a default client. Then we build a request using the builder, passing in a URI, saying that it should be a GET request, then building the request. And then we can just call HTTP client.send, pass in the request. And the only thing that's new here is the body handler, which tells the HTTP client how to turn the response into something that we can use in our code. And this is a simple handler that translates into a string, but there are others as well. So this is a really useful addition, at least in my opinion, to Java. Because Java itself is adopting a rapid release schedule, you see that the amount of new features in each release is decreasing as well, which is good because it helps us adopt. But what about the adoption of Java? Because, well, we saw most of the room here is still using Java 8, and you know what? You're not alone, because these polls, as of 2018, indicate that 8 out of 10 developers are still using Java 8, and the others are either using an earlier version or a newer version, sort of 50-50 for the remaining people. And this is visible across the board. This is JetBrains research. There's a Java Magazine poll. Also, 8 in 10 developers are using Java SE 8. So this is actually really an issue. Even Red Hat, who maintains an OpenJDK port, has said that they will skip Java 9 and Java 10 and will jump right to distributing Java 11. So why is that? The Java 11 release schedule fits in this picture. So we get a new release of Java every 6 months. So we got Java 9, we got Java 10, and we saw that the adoption was quite low. So why would Java 11 be different? Well, yeah, of course, it goes to 11, and we're all rockstar programmers, so we can appreciate that. But that's not the actual reason. The reason is long-term support. And what happened is that Oracle announced that every 3 years they will designate one Java version as long-term supported, which means that Oracle at least has committed to supporting this version for at least 3 years. And Java 11 is such a long-term support version. Java 17 will be the next one in 3 years from now. And in between, we will get Java 12, 13, 14, etc., etc. And each of these releases is a major release in the sense that it can contain new features, it can deprecate features, it can remove APIs after they have been deprecated. So this is really the moment to start thinking about a strategy to handle this as a company, as a development team. Because on the one hand, it might sound safe to stay on the LTS version and just wait until Java 17 is there and then make the move. But the world is moving so quickly, and there's lots and lots of features coming up in the pipeline for the coming versions of Java. So it also seems a bit dumb to adopt that strategy. So what are you going to do? That's really not something that I can answer for you. The only thing that I can say is that there will be a release every 6 months. It will not be as big as Java 7, Java 8, and Java 9 because it's just there's less time to create new features. But there will be a release train that you need to keep track of, either by using it or at least by getting knowledge about what's in there, so you're prepared if you move from LTS to LTS. Also, one misconception about long-term support is about whether this is long-term support in OpenJDK or in the Oracle JDK, because these are two different things. And actually, what's currently happening in Java 8 is that most people are using the Oracle JDK, and not that many people are using the OpenJDK distribution, which is fine for Java 8. But as of Java 11, the licensing terms for Oracle JDK have changed into a commercial one. So if you're using Oracle JDK and you're jumping to Java 11, you cannot use Oracle JDK in production without having a subscription with Oracle. And that might sound really horrible, but it's really not, because what Oracle did is they made sure that OpenJDK and Oracle JDK are, as of Java 11, identical in the sense that they're feature for feature the same. That means that a lot of stuff that was proprietary in the Oracle build, that gave the Oracle build some edge in terms of performance, etc., has all been open sourced or cut out of the JDK. Things like WebStart are gone, for example. And so this way they reached feature parity between OpenJDK and the Oracle JDK. But it does mean that if you're moving from Java 8 to Java 11, you should seriously look at OpenJDK. Again, there are plain OpenJDK builds from the OpenJDK website. There are also other parties offering OpenJDK builds, for example, Azul and IBM are doing so. And there's even a community effort called Adopt OpenJDK, which offers a JDK build. But the interesting thing is that the guarantee about long-term support only holds for Oracle JDK 11, and therefore only is available if you're going to pay Oracle a subscription fee. And what happens with OpenJDK 11 isn't quite clear yet. There are some parties that have stepped up and said, okay, we're going to also do long-term support for OpenJDK 11, and Red Hat is one of these parties, but well, we all know that Red Hat got bought by IBM last week, so who knows what happens there. This is definitely something to keep your eye on and to start watching. And again, if you're just following the release train, if you're going from Java 11 to 12 to 13, etc., then this whole discussion doesn't really matter. Then you can just keep using the plain OpenJDK builds and be sure that you have a stable, secure, and patched build. It's only if you want to jump from LTS to LTS that you need to start thinking about a strategy of adopting a certain vendor's JDK. Maybe it's Oracle, maybe it's Azul, maybe it's Adopt OpenJDK, maybe it's Red Hat, But this is really something that's changing as of Java 11. So that's all I wanted to share with you guys about what's up in Java, and I hope this was useful to you. Maybe we'll also have some questions, Jörg, I don't know, but now would be a good time to see.